If you look at the circuit, okay, let me draw the circuit. So, I will come to the expression of IV. So, I have 3 legs. So, I have the current IA shown as leaving the positive terminal of EA, then IB, IC. So, this is 1, 3, 5, 4, 6, 2, VD is here. So, IB is a current that flows, or it has a non-zero value if and only if valve 3 is conducting or valve 6 is conducting. See, it is either equal to I3 or minus I6. One can say that it is I3 minus I6. Say by Kirchhoff's current law, it is I3 minus. See, the current through the valve 3 is I3, current through the valve 6 is I6. So, IB, I am not worried about IA or IC right now. So, if I just look at IB, it is I3 minus I6. Okay. Now, we also saw that there are 6 intervals and 12 sub intervals. So, if you look at the table, the first sub interval is from alpha to alpha plus u, alpha plus u to alpha plus 60 degrees. Say these are the values of omega OT, alpha plus 60 degrees to alpha plus u plus 60, alpha plus u plus 60 to alpha plus 120, alpha plus 120 to alpha plus u plus 120, alpha plus u plus 120 to alpha plus 180, alpha plus 180 to alpha plus u plus 180, alpha plus u plus 180 to alpha plus 240, alpha plus 240 to alpha plus u plus 240, alpha plus u plus 240 to alpha plus 300, alpha plus 300 to alpha plus u plus 300, alpha plus u plus 300 to alpha plus 360. So, these are the 6 intervals, and in which there are 12 sub intervals. So, we know what are the valves that conduct. So, if you take the first sub interval, the valves that conduct are 1, 2, 3. The second sub interval, it is 2, 3, then 2, 3, 4, then 3, 4, 3, 4, 5, 4, 5, 4, 5, 6. We have already formed this table. I am just trying to again use this information. Say the table had some more information that actually we don't need for analyzing the AC side current. Then 5 6 5 6 1 6 1 6 1 2 1 2. Okay. Now there is one type of symmetry on the AC side. On the AC side, if you look at the currents are identical except for a phase shift of 120 degrees. So if you take IB of omega OT, then it is nothing but IA which is delayed by 120. So it is omega OT minus 120. IA of omega OT minus 120 will give me IB. Similarly, if you take IC of omega OT, it is IB delayed by 120. So IC of omega OT is IB of omega OT minus 120. Now if you look at the currents through the valve, say if you take any current, say I can have a current through valve 1 which is I1, current through valve 2 which is I2, current through valve 3 is I3, current through valve 4 is I4, current through valve 5 is I5. Now I will try to use one fact which I think we are all familiar with. What do you expect for these 6 currents I1, I2, I3 up to I6? Are they same, similar, identical with phase shift? Can we say anything about that, or we can't say anything? They are different? Do they satisfy some condition? I1, I2, I3, I4, I5, I6. See, please note, we derived this from a very general circuit. Say, this circuit is not obvious. This is the great circuit. See, 6 legs, 3 legs, 6 devices, and 3 AC side terminals, 2 DC side terminals is something which is not an obvious circuit. Okay, it was derived in fact from something which was more obvious. So this is known as the great circuit. So here there are 6 devices, and I take all the currents which are flowing from anode to cathode. All the 6 currents are shown as flowing from anode to cathode. So what do you say? If you go back to the derivation, do you see that there is some pattern in these currents? Are they identical except for phase shift? Do you see that? Because if you go back to the derivation, these devices are connected in series with voltage sources. So there are 6 voltage sources connected in series with these 6 devices, and these 6 voltage sources are actually identical with a phase shift of 60 degrees. So if you take the 6 voltages, they are all identical voltages, and phase shift between them is 60 degrees. So these currents are also actually identical with a phase shift of 60 degrees. Now you see that the sequence of turning on is 1, 2, 3, 4, 5, 6. See, the numbering is in such a way that they are in the order of turning on. Okay. So that means I1, I2 up to I6 are identical, except that there is a phase shift between the any 2 currents. If I take I2, it is identical to I1 except that there is a delay of 60 degrees. Similarly, I3 is identical to I2 except for a delay of 60 degrees. So if I take I1, it is related to I2. So if I take I2 for example, I2 of omega OT, can I say that it is equal to I1 of omega OT minus 60 degrees? And if I take I3, it is nothing but I2 minus 60 degrees, I2 of omega OT minus 60 degrees, then I4 of omega OT is I3 of omega OT minus 60 degrees, then I5 of omega OT is I4 of omega OT minus 60 degrees, then I6 of omega OT is I phi of omega OT minus 60 degrees. And of course, I1 of omega OT will be I6 of omega OT minus 60 degrees. Okay. So, what we have is identical currents in the valves except for a phase shift of 60 degrees. And of course, I can also relate in each leg the valve currents and the current on the AC side. Just as I have related I3, I6 and IB, I can relate I1, I4 and IA. I can also relate I5, I2 and IC. Okay. So, but I am not going to do that. I mean, that is just application of Kirchhoff's current law. What I will do is I will just restrict myself to this IB, one of the phase currents. So, I am interested in the expression of IB. So, IB as a function of omega OT. Okay. Let us try to get the expression in all the 12 subintervals. So, we are interested in all the 12 subintervals. Okay. So, the first subinterval is alpha to alpha plus u. So, what is IB from alpha to alpha plus u? See, from alpha to alpha plus u, 1, 2 and 3 are conducting, valves 1, 2 and 3 are conducting. So, IB is dependent only on the current through either 3 or 6. So, whether 1 or 2 conduct does not matter. So, IB is equal to I3, I6 is 0 because I6 is not conducting. So, IB is I3 in the first subinterval, and we got the expression for I3. Okay. So, we derived the expression for I3, it is ID cos alpha minus cos omega OT. So, this is the expression for IB in the first subinterval alpha to alpha plus u. Okay. Oh, sorry, I am sorry, please correct this, it is IS, sorry, it is IS into cos alpha minus cos omega OT. IS is the short circuit current. Then, if I take the second subinterval alpha plus u to alpha plus 60 degrees, the current IB is equal to the current I3. Now, please note that in the next subinterval alpha plus 60 to alpha plus u plus 60 also, I have only valve 3 conducting in the upper commutation group. See, upper commutation group is 1, 3, 5. See, when only 3 is conducting among 1, 3, 5, IB is equal to I3. Okay. So, please note in any of if you look at this 12 subintervals, is there any subinterval where both 3 and 6 conduct? There is no subinterval where both 3 and 6 conduct. So, its IB is either equal to I3 or equal to minus I6. Okay. So, based on this information, I can say that IB is either equal to I3 or IB is equal to minus I6. I can say easily. Of course, this also covers the case of I3 being equal to 0 as well as I6 being equal to 0. See, there are some subintervals where neither, is there a subinterval? See, there is a subinterval where only 4 and 5 conduct. So, when 4 and 5 conduct, neither 3 is conducting nor 6 is conducting. That means both I3 is 0, I6 is also 0. So, I can still use this relation that IB is either equal to I3 or equal to minus I6. Okay. So, if you look at the subintervals 2, 3 and 4, subintervals 2, 3 and 4, there is only one valve that conducts in the upper commutation group, that is valve 3. Valve 3 is the only one which is conducting among 1, 3, 5 from alpha plus u to alpha plus 120. Okay. So, that means for alpha plus u to alpha plus 120, IB is equal to ID. So, it is equal to ID for alpha plus u to alpha plus 120. Now, one can easily observe one fact that unlike the previous case where L was 0, here L is non-zero, IB cannot have discontinuities. So, when IB cannot have discontinuities, then I can easily say what happens at omega t equal to alpha, what happens at omega t equal to alpha plus u. Okay. So, I can replace the strict inequality by less than or equal to. Now, this was not possible in the previous case where L was 0. See, there were discontinuities in the current. Now, IB will never be discontinuous because of the presence of L, non-zero L. Okay. So, that is the expression for IB up to alpha plus 120. Then, in order to get the next expression, see the next subinterval is alpha plus 120 to alpha plus u plus 120. So, in this case, what is the expression for IB? How to get the expression? So, we saw that. So, just in the previous page, IB of omega OT is actually IA of omega OT minus 120. So, if I know what happened to IA 120 degrees ago, I can find IB now. That is what it means. Okay. So, I know what happens for alpha to alpha plus u. See, I am interested in, okay, let me tell you, I am interested in the expression for IB from alpha plus 120 to alpha plus u plus 120. Now, this subinterval is nothing but the first subinterval shifted to the right by 120 degrees, okay, shifted by 120 degrees. That means, you get the take the expression for IA in the subinterval alpha to alpha plus u, shift, if you shift that by 120 degrees, you get the expression for IB. I think I need to use one more equation. So, what is what is IA? Say, I do not have the expression for IA here in the interval alpha, in the subinterval alpha to alpha plus u. What I have is the expression for IB from alpha to alpha plus u. So, if I know IA from alpha to alpha plus u, shift it by 120, I get the expression for IB. So, what is the expression for IA from alpha to alpha plus u? Yeah. So, for alpha less than or equal to omega OT less than or equal to alpha plus u, IA of omega OT is nothing but ID minus IB of omega OT. So, I know the expression for IA. Now, I use this equation, IB of omega OT is equal to IA of omega OT minus 120. So, if I do that, I get the expression for IB as ID minus IS into cos alpha minus cos omega OT minus 120 degrees. Okay. So, is that okay? So, we got the expression for IB up to alpha plus u plus 120. Then what happens after that? So, come back here, alpha plus u plus 120. After alpha plus u plus 120, the next subinterval is the one where only 4 and 5 conducts. When 4 and 5 conducts, IB is 0. So, when 4 and 5 conducts, IB is 0. So, that 0 value of IB holds up to alpha plus what? 180. So, it is equal to 0 for alpha plus u plus 120 less than or equal to omega OT less than or equal to alpha plus 180. Then after that what happens? So, the next interval is alpha plus, next subinterval is alpha plus 180 to alpha plus u plus 180. Alpha plus 180 less than or equal to omega OT less than or equal to alpha plus u plus 180. So, what should be the expression for IB? Yeah, what is that equation that we use to arrive at that? How do you say it is minus of? Okay. So, if you take this subinterval alpha plus 180 to alpha plus u plus 180. So, which value is conducting? 4, 5, 6. So, IB is equal to minus I6. Okay, let me first write that. So, for alpha plus 180 less than or equal to omega OT less than or equal to alpha plus u plus 180 degrees, IB of omega OT is equal to, just now we saw. So, in this subinterval 4, 5 and 6 conduct. So, when 4, 5 and 6 conduct, IB is equal to, see, in general it is I3 minus I6, but I3 is 0, 3 is not conduct. So, it is minus I6. So, it is minus I6 of omega OT. Now, what is the use of having minus I6? I mean, what is, I mean, is there any purpose served in having minus I6? Yeah, I6 is related to I3. So, I6 is identical to I3 except for a phase shift of, yeah, go back to the, say, in the last line I have the phase relationship between I1, I2, I3, I2, I4, I3, I5, I4, I6, I5. So, from that can I get the relationship between I6 and I3? So, I6 is identical to I3 except for a phase shift of 180 degrees, 60 into 3. So, 180 degrees. So, what does that mean? It is minus I3. So, or in other words, okay, I can write it as minus I3 of omega OT minus 180 degrees. I3 and I6 are identical except for a phase shift of 180 degrees. Okay. Now, do I have the expression for the, now I need the expression for I3 for which subinterval? Say I am current subinterval of interest is alpha plus 180 to alpha plus u plus 180. So, I want to know what happened to I3 180 degrees ago. That means which subinterval? Yeah, you just subtract 180 degrees from the upper and lower limits of omega OT. So, from alpha to alpha plus u, what happened to I3? We should know. So, do we have the expression for I3 from alpha to alpha plus u? It is nothing but IB. It is nothing but IB. So, what I have to do is just take the expression for IB from alpha to alpha plus u. Yeah, it is not difficult. I mean, it just takes some it requires some concentration, nothing more than that. Okay. So, okay, let me write that also. So, can I say it is minus IB of omega OT minus 180 degrees? IB is equal to I3. Is that okay or not? Okay. So, now we have this expression. So, this is equal to minus IS into cos alpha minus cos omega OT is there. I should replace that by cos omega OT minus 180 degrees. So, this is nothing but minus IS cos alpha plus cos omega OT. So, I will just write this expression here, minus IS cos alpha plus cos omega OT. So, this expression is applicable from alpha plus 180 to alpha plus u plus 180. Then, is this clear? Then we will go to the next subinterval, alpha plus u plus 180. So, at alpha plus u plus 180 degree, valve 4 stops conducting. So, 5 and 6 conduct. So, when just 5 and 6 conduct, then IB is equal to minus ID. IB is minus ID. Now, you see that even in the next subinterval, though there are 3 valves 5, 6, 1 conducting, in the lower commutation group only 6 is conducting. From alpha plus 240 to alpha plus u plus 240, 5, 6, 1 conduct. So, only 6 is conducting in the lower commutation group. The same thing happens even in the next subinterval alpha plus u plus 240 to alpha plus 300, 6 and 1 are conducting. So, as long as only 6 is conducting among 2, 4, 6, IB is equal to minus ID. Okay. So, that happens from alpha plus u plus 180 degrees to alpha plus 300. Okay. So, the expression is minus ID for alpha plus u plus 180 degrees to alpha plus 300 degrees. Is that okay? Because from alpha plus u plus 180 to alpha plus 300, only valve 6 conducts among the valves 2, 4, 6. So, anyhow valve 3 is not conducting. So, IB is minus I6, which is minus ID. Right. Now, let us take the next subinterval. The next subinterval is alpha plus 300 less than or equal to omega OT less than or equal to omega less than or equal to alpha plus u plus 300. So, in this subinterval, so if you look at this subinterval alpha plus 300 to alpha plus u plus 300, valves 6, 1 and 2 are conducting. So, when valves 6, 1 and 2 are conducting, then what is IB? Of course, it is minus I6. IB is minus I6, but how do you get that? I mean, what is the use of that? Okay, let me write it. For alpha plus 300 to alpha plus u plus 300. IB of omega OT is equal to minus I6 of omega OT. Now, again we use the same result, that I6 of omega OT is equal to I3 of omega OT minus 180 degrees. So, it is minus I3 of omega OT minus 180 degrees. Now, this can be written in terms of IB. So, can I say that this is minus IB of omega OT minus 180 degrees? So, we know the expression for IB in the, so which subinterval we have to look at for IB? See, the current subinterval of interest is alpha plus 300 to alpha plus u plus 300. So, for this subinterval we are getting an expression for IB. So, this is in terms of IB which was obtained for a subinterval which was 180 degrees ago. So, which one? It is alpha plus 120 to alpha plus u plus 120. So, we have the expression for IB from alpha plus 120 to alpha plus u plus 120. So, this is equal to minus ID plus IS cos alpha minus cos, in place of omega OT I have omega OT minus 180 degrees. So, this can be simplified. So, this can be written as minus ID plus IS into cos alpha. So, minus cos omega ot minus 180 minus 120 is plus cos omega ot minus 120. Is that okay? So, this is the expression up to alpha plus u plus 300. Then, if I go to the next subinterval, it is alpha plus u plus 300 less than or equal to omega ot less than or equal to alpha plus 360 degrees. So, in this subinterval alpha plus u plus 300 to alpha plus 360 degrees, valves 1 and 2 are conducting. So, neither 3 is conducting nor 6 is conducting. So, IB is 0. So, this is 0. Okay. So, we have the expression for IB for one full cycle from alpha to alpha plus 360 degrees. Of course, though there are 12 subintervals, some expressions are applicable for multiple subintervals, that is why we have only 8 expressions. Of course, some of them are, say it is 0 for 2 of these subintervals also. Now, if I want to find the fundamental component RMS value or harmonic component RMS value, I have to do Fourier series, but any simplification is possible. Do you see any symmetry in IB? It has half wave symmetry. So, IB of omega ot plus 180 degrees is equal to minus IB. So, you see that this has half wave symmetry. So, IB has half wave symmetry. So, what does that mean? I need not use the entire expression from alpha to alpha plus 360. I can just use the expressions applicable to one half of the cycle, say alpha to alpha plus 180, that is sufficient. So, I can just use, say for example, these 4 expressions, do Fourier analysis and get the RMS value of the fundamental as well as harmonics. So, I will leave that to you. So, I will give the answer. RMS value of fundamental component this is a very good example to know that how laborious it can be to apply Fourier analysis. Okay, this actually this particular example, of course, I took some long time to get this. RMS value of fundamental component of AC side current. So, I use the notation I with a subscript 1. So, the expression is root 6 ID by 2 pi into square root of cos alpha plus cos alpha plus u whole square plus 2u plus sin 2 alpha minus sin 2 alpha plus 2u divided by 2 cos alpha minus 2 cos alpha plus u. See, the main point here is if you apply Fourier series for such a waveforms, you get an expression which is 2 page or 3 page longer. I mean only the main work involved is simplification. do some trigonometric manipulations and simplify. That's all. See, once you integrate, after integration your expression will be very long, I mean maybe 1 or 2 pages long. So, after simplification you get this. Okay. So, that is the idea. So, this is the fundamental component. Now, what are the harmonic components? I mean, what is the order of the harmonic components that are present? See, there is half wave symmetry. So, due to half wave symmetry, you will not have even harmonics. You will not have even harmonics due to half wave symmetry. Second harmonic, fourth harmonic, sixth harmonic are not there. Any other harmonic is not there. Third harmonic, triplen harmonics. Why? Yeah, because IA plus IB plus IC is 0. So, triplen harmonics are also not there. So, the harmonic components are of order 5, 7, 11, 13, 17, 19. So, the harmonic components in the AC side currents are of order H equal to 6k plus minus 1, where k takes all positive integer values. Okay. So, if you put k equal to 1, you get 5 and 7, k equal to 2, you get 11 and 13, so on. Okay. So, these are the order of the harmonics. So, what is the expression? Again, you have to apply Fourier analysis to get the expression for the RMS value of the harmonic component. So, for H equal to 6k plus minus 1, k equal to 1, 2, 3, so on, the RMS value of Hth order harmonic component in AC side currents. Of course, for other values of H it is 0. So, I will use the notation IH. So, it is root 6 ID by pi H into sine square H plus 1 u by 2 divided by H plus 1 whole square plus sine square H minus 1 u by 2 divided by H minus 1 whole square plus minus 2 sine H plus 1 u by 2 sine H minus 1 u by 2 cos 2 alpha plus u divided by H square minus 1. This entire thing is taken under root. This is divided by cos alpha minus cos alpha plus u. So, that is the expression. Of course, so there can be one obvious question, why I am writing separate expression for I1 and for IH where H is not equal to 1. See, Fourier series does not distinguish between H equal to 1 and other values of H. Now, the purpose of writing two expressions is to say that I can't use the general expression for IH for I1. Why I can't do that? I mean, that is for you to answer. So, you can try, say, instead of trying to get first I1 and then IH, why don't you see, I mean, in the expression for IH, actually it's obvious, there is a H minus 1. So, that is why I can't use that. So, there is some problem in using this expression for IH when H is equal to 1. Okay. So, this expression is applicable only when H is not equal to 1. So, for I1 you have to do a separate derivation.